If your vulnerability scanner alerts you to 10,000 critical vulnerabilities right this second, how do you mathematically prove to your CISO or, your board of directors which 10 you need to patch today before you go home?
Right. It's the ultimate question.
Yeah, I want you to really genuinely think about that for a moment. How do you prove it? Because right now, the industry is just relying on a whole lot of guesswork dressed up as objective metrics. And honestly, it is completely breaking our teams.
It absolutely is.
Just looking at the recent telemetry across the industry from the research, we have just crossed this massive, staggering threshold. The National Vulnerability Database, the NVD, is now past 308,000 total published CVEs.
Which is just a wild number to even conceptualize.
It is, and based on current trajectory projections in the research, we're expecting another 48,185 new ones to drop in 2025 alone. That's a 20.6% year-over-year growth rate.
Yeah, exponential growth, basically.
Exactly. So security teams are absolutely drowning in a sea of red alerts. We are seeing a complete crisis of alert fatigue, analyst burnout, and frankly, just a lot of misplaced anxiety.
Oh, the anxiety is palpable. You talk to any SOC analyst and they're stressed.
Right. And this exact situation, this completely unsustainable pressure on intermediate and senior security professionals, is exactly what prompted today's deep dive into the research.
It's a very timely deep dive, that's for sure.
So today we are breaking down the Exploit Prediction Scoring System, or EPSS. We're going to look deeply at the research, dissect the machine learning model right behind it, and build a framework to transform your vulnerability management from a panicked guessing game into, well, a precise data-driven science.
I love that framing because
Yeah.
it really is a critical breaking point for the industry right now.
Hmm?
We are watching entire security operations centers just buckle under the sheer weight of the math.
Yeah, the math just doesn't add up anymore.
It doesn't. You simply cannot outwork a 20% compounding annual growth rate in vulnerabilities using, manual triage and static severity scores. It's a fascinating, albeit terrifying data problem.
Terrifying is the right word.
But let's set the baseline right here at the top for you listening. EPSS is an incredibly powerful tool. It is radically reshaping how the most mature organizations handle threat intelligence. But it is not magic.
Right, it's not a crystal ball.
Exactly. It's applied statistics. It's a probabilistic model. And like any statistical model, you need to understand exactly what data is going into it and, crucially, what its limitations are to actually get real operational value out of it.
I think that's the perfect place to start. We have to understand the math of the problem before we can look at the math of the solution. Let's really unpack what we're dealing with regarding this vulnerability pandemic.
Let's do it.
Because looking through the research, specifically the data from the Scientia Institute and Security Scorecard, it paints a stark, almost impossible picture of the status quo.
It really does. Let's just lay out those numbers because they are the foundation of why our current decision models are just completely broken.
Go for it.
Right now, there are roughly 78 new software vulnerabilities published every single day.
Wait, 78 every day?
Every single day. That translates to over 20,000 to 30,000 new CVEs added to the public record annually. Now, look at the other side of the equation, enterprise remediation capacity.
Oh, boy.
Yeah, studies from across the industry show that remediation capacity, which is a team's actual ability to test, deploy, and verify patches, is basically stagnant. On average, organizations are only capable of patching roughly 5% to 15% of their total vulnerability backlog each month.
I want to pause right there and emphasize that for you listening, because if you are an infrastructure architect or a SOC analyst or a GRC professional, you are probably feeling a low-level constant guilt that your backlog is perpetually growing.
Oh, absolutely. Everyone feels that guilt.
But you shouldn't. The data shows everyone is in the exact same boat. You can only fix 10 to 15% of your backlog a month, but the pile is growing by 20% a year. The math is structurally impossible.
Structurally impossible. I like that.
More threats arrive daily than your security teams can possibly address monthly. It is just compounding technical debt. And yet, how are we told to prioritize this impossible mountain?
By using CVSS.
Right, by using CVSS.
And this reliance on CVSS, the Common Vulnerability Scoring System, is probably the most widely misunderstood practice in our field today.
Which is saying something, because there are a lot of misunderstood practices.
Fair point. And to be fair to CVSS, it was introduced back in the early 2000s with very good intentions. It was meant to standardize how we talk about vulnerabilities.
Give everyone a shared language.
Exactly. It gave us a shared taxonomy. But it was designed to measure technical severity in a vacuum. It measures the worst-case scenario impact if a vulnerability were to be exploited. It does not. It was never intended to measure real-world threat likelihood.
Right. And just to throw in a quick host note here for the listener, CVSS is a framework for rating the inherent severity of a software flaw, but it lacks dynamic threat context. It doesn't know what's happening on the internet right now.
That's the perfect way to summarize it.
To use an analogy, because I think the way we talk about CVSS is just so fundamentally broken, judging your risk purely by a CVSS score is like grading a bomb by its explosive yield without checking if it actually has a detonator.
Oh, I like that.
Right. You're looking at a piece of software and saying, wow, if an attacker gets in here, they get root access, they bypass authentication, they can steal all our data. That's a 9.8 critical.
Red sirens everywhere.
Exactly. But you aren't asking the operative question, is anyone actually writing the code to exploit this? Does a detonator exist?
That is a brilliant way to frame it. Technically, CVSS does have temporal and environmental metric groups that are supposed to add that kind of context. You know, things like whether exploit code is publicly available.
But no one uses those.
Right, let's look at operational reality. The vast majority of organizations and commercial vulnerability scanners just consume the base NVD score. They pull the API, they see a 9.8, and they trigger a critical alert.
And then the pagers go off at 2 a.m.
Exactly. So you end up with a static number that completely fails to adapt to post-disclosure threat intelligence.
And the data on the resulting alert fatigue is wild. I mean, over 57% of all CVEs are flagged as high or critical by CVSS. Think about that for a second.
It's more than half.
More than half of every vulnerability ever discovered is categorized as high or critical. If everything is critical, nothing is critical. It entirely defeats the purpose of triage.
It really does. It becomes white noise.
But here is where it gets really interesting. The research shows that only 2.3% of vulnerabilities with a CVSS score of 7 or higher actually see exploitation attempts in the wild.
2.3%.
2.3%. And to flip that on its head, 28% of the CVEs that are actually exploited in the wild, the ones being used by ransomware gangs today, only carry a medium CVSS score.
Which perfectly illustrates the disconnect. That 28% is the blind spot that gets companies breached.
Yep.
We have intermediate analysts and security engineers spending their entire weekends patching a CVSS 9.8 in a highly segmented internal development container that has absolutely no internet access.
Just because of a compliance mandate.
Exactly.
Yeah.
Simply because of compliance mandates tied strictly to that base score.
Meanwhile, an internet-facing production web server has a CVSS 6.5 vulnerability.
Right, just a medium.
It doesn't look scary on paper, but it is actively being weaponized by threat actors globally, and it gets completely ignored by the security team because it didn't trip the critical filter in their management dashboard.
It's madness. Prioritizing purely by CVSS base scores is statistically equivalent to picking vulnerabilities out of a hat. You're just randomly guessing based on hypothetical worst-case scenarios. It's a very expensive guessing game.
So to ground this for you listening, think about it like this. Imagine CVSS as your building's structural integrity report. It tells you if your house is made of paper, wood, or solid brick.
Which is good information to have.
Definitely good to know. But EPSS, the exploit prediction scoring system, is the weather forecast. It tells you if a Category 5 hurricane is actually hitting your specific block tomorrow.
I love the weather analogy.
Right, because you do not evacuate the entire neighborhood for a paper house if it's perfectly sunny outside. But you absolutely urgently reinforce the brick house if you know a tornado is inbound.
That distinction is everything. If we connect this to the broader evolution of risk management, the shift from CVSS to EPSS is a fundamental shift from measuring potential impact to measuring actual predictive risk.
Moving from hypothetical to empirical.
Yes, we are moving from a hypothetical framework to an empirical framework.
Okay, so that perfectly sets up our transition into the solution space. Let's really demystify EPSS. What exactly are we dealing with here? What is the architecture of this system?
So EPSS is an open, data-driven, machine learning-backed model. It is managed by, first, the Forum of Incident Response and Security Teams.
Wait, isn't FIRST the same group that does CVSS?
It is, which is deeply fascinating and somewhat ironic. The exact same governing body that manages CVSS manages EPSS.
Oh, that's wild. So they knew CVSS wasn't enough.
Exactly. The creators of the severity score recognized the gap themselves. They realized the industry desperately needed a likelihood score.
Makes sense.
The model's primary output is straightforward, though the math behind it is quite complex. It provides the near-term probability that a specific software vulnerability will be exploited in the wild within the next 30 days.
And crucially, it refreshes daily. That is a massive distinction from CVSS, which is generally, static.
Very static.
Right. A CVSS score is assigned, and unless there's a massive reevaluation, it just sits there for a decade. EPSS updates every 24 hours based on shifting global telemetry.
Which changes the whole game.
So as a security professional, you query the API or you download the daily CSV file, and it gives you two main decimal breakdowns for every published CVE, a probability score and a percentile rank. Let's break those down.
Sure. So the probability score is a raw output value ranging from 0.0 to 1.0. Think of it strictly as 0% to 100%.
Simple enough.
Right. So if a CVE has an EPSS of 0.96, the model is predicting a 96% chance of exploitation activity occurring somewhere in the world against that vulnerability in the next 30 days.
Okay, got it.
The percentile rank, on the other hand, is a relative metric. It compares that specific CVE's probability to all other active CVEs that the model scores.
Okay, wait. I need to play devil's advocate here for a second, or at least express a little bit of the confusion I felt the first time I looked at these numbers.
Go for it.
Let's say my vulnerability scanner flags a CVE on an Apache server, and the EPSS API tells me it has a probability score of 10%, just 0.10. If I take that to my infrastructure team and I tell them to drop everything, schedule emergency downtime, and patch a production server for a 10% chance of rain, they are going to literally laugh me out of the room.
They absolutely would.
A 90% chance of nothing happening doesn't sound like an emergency at all. Why would I care about a 10% probability?
It's a very common, very human reaction, and it touches on a classic cognitive bias. What you're experiencing right there is the base rate fallacy.
The base rate fallacy.
Yeah. We are conditioned to think of 10% as a failing grade or a totally negligible chance because we assume the baseline probability of things happening is much higher.
Like a coin flip.
Exactly. We think of a coin flip, which is 50-50.
Right. So for the listener host note here, the base rate fallacy is this cognitive error where we ignore the overall background frequency of an event, which is the base rate, when we are evaluating specific probabilities. We just look at that 10% in total isolation.
That's exactly it. To understand why 10% is actually alarming in this context, we have to look at the global base rate of software exploitation.
Okay, lay it on us.
The empirical research is incredibly clear on this. Out of hundreds of thousands of published CVEs in the National Vulnerability Database, only about 5% are ever exploited in the wild.
Ever, like in their whole lifespan.
Ever. That 5% is your lifetime base rate for all vulnerabilities. So when EPSS gives a specific vulnerability a 10% probability of being exploited just within the next 30 days, that is actually double the lifetime average of a normal vulnerability.
Oh, wow. Okay. When you frame it like that, it changes the entire perspective. So in the context of global software vulnerabilities, an EPSS of 10% is actually screaming hot.
Precisely. And this is exactly why FIRST provides that second metric, the percentile rank. If you look at the percentile rank for that same vulnerability with a 10% absolute probability, you'll see it sits right around the 88th percentile.
So it's in the top tier.
It means a 10% chance of exploitation puts that threat in the top 12% of the most dangerous, highly targeted vulnerabilities globally.
That's a huge difference in messaging.
It is. This is why FIRST strongly recommends looking at the percentile to give your engineering and operational teams that localized context. A 10% absolute probability might not sound scary in a vacuum, but knowing it's in the top 12% of all global threats completely changes the priority conversation.
The data truth here is wild when you actually visualize it. When you look at the distribution curve in the research, it is this massive, extremely heavy long tail.
The long tail is fascinating.
Roughly 88% of all CVEs sit at or below a 10% probability, and the vast, vast majority of them sit at a literal 0%. It's an enormous mountain of vulnerabilities that just never go anywhere. They're pure academic exercises.
And that long tail is exactly where the alert fatigue lives. That's where all the wasted engineering hours go. Security teams are chasing CVSS 8s and 9s that live deep in that 0% probability tail.
Burning out for no reason.
Exactly. They are burning social capital with their IT operations teams, demanding emergency patching windows for vulnerabilities that no attacker on Earth is actually utilizing.
Let's just pause and let you, the listener, internalize that. Think about those tens of thousands of vulnerabilities your scanner is yelling at you about right now. Think about the CSV exports that literally crash Excel when you try to open them.
We've all been there with the frozen Excel screens.
Right. The hard empirical research from honeypots and threat intel feeds globally proves that the vast majority of those vulnerabilities will never, ever be weaponized against you. They are theoretical ghosts.
Just ghost in the machine.
You can breathe a little. You don't have to patch everything today. You just have to patch the right things.
Which naturally leads us to the most critical operational question. How does the model actually know what the right things are?
Yes.
If we're going to trust this system to ignore 80% of our backlog, how does it generate these predictive probabilities?
I was just about to ask that. We need to look under the hood of the ML engine. Security pros, by nature, we absolutely hate black boxes. We are skeptical people.
Highly skeptical.
If I'm going to bet my company's weekend on a machine learning model telling me not to patch a CVSS critical, I want to know exactly what that model is eating. What are the ingestion pipes looking at?
It's an incredibly robust and diverse data diet. The model ingests over 1,400 distinct features to make these daily predictions.
1,400.
1,400. It's not just looking at one or two simple indicators. Broadly, the data falls into a few categories. First, it looks at the vulnerability metadata. It scrapes text descriptions, vendor tags, and weakness enumerations from the OMITRE ACVE list. It looks at the age of the vulnerability.
Okay, so static data.
Right. Then it looks at the attacker ecosystem. It actively monitors public exploit code repositories, places like GitHub, ExploitDB, and the Metasploit framework. If a proof of concept exploit drops on GitHub, EPSS ingests that signal.
Wait, hold on. I need to push back here. 1,400 features. In traditional machine learning, if you throw 1,400 random features at a model, text descriptions, GitHub commits, vulnerability age, doesn't that just create a massive amount of noise?
It definitely can.
Doesn't the model just overfit and start finding false correlations? Like, oh, vulnerabilities published on a Tuesday with the word buffer in them are 90% likely to be exploited. How does it actually make sense of that much unstructured data without hallucinating?
That is the exact right question to ask, and it's why the architecture of the engine is so incredibly important.
Yeah.
You are absolutely right that a simple linear regression model would completely choke and overfit on 1,400 features.
It would just be garbage in, garbage out.
Exactly. But let's look at how the engine has evolved. We are currently on EPSS version 3. Version 1 used an algorithm called ElasticNet, which struggled with exactly what you were describing. It couldn't handle highly complex nonlinear relationships. But for version 3, they transitioned to an entirely different framework utilizing XGBoost and gradient boosted trees.
Okay, let's unpack that because not everyone listening is a data scientist. What makes gradient boosted trees so much better at filtering out the noise of those 1,400 features?
Sure. Think of gradient boosted trees as an ensemble of very specialized, narrow-minded analysts.
Narrow-minded analysts, I like it.
Instead of building one massive, complex algorithm to predict everything at once, it builds hundreds of simple decision trees. A decision tree might just ask a simple question, is there exploit code in Metasploit? Yes or no?
Very binary.
Right. The boosting part means it builds these trees sequentially. The first tree makes a prediction, and it inevitably gets some wrong.
Naturally.
The second tree is then built specifically to focus on correcting the errors of the first tree. The third tree focuses on the errors of the second. It iteratively learns from its mistakes, optimizing for accuracy.
So for the listener host note here, gradient boosted trees are essentially a machine learning technique that builds an ensemble of weak prediction models, optimizing them sequentially to improve accuracy. It's basically a self-correcting feedback loop.
Exactly.
It's not just taking all 1,400 features and mashing them together. It's using them conditionally to refine its own guesses.
Spot on. XGBoost is exceptional at figuring out which of those 1,400 features actually matter and ignoring the noise. It can spot subtle, non-linear relationships.
Like what? Give me an example.
Well, for example, it might learn that having a proof of concept on GitHub only matters if the vulnerability is also remotely exploitable and if it affects a widely deployed operating system.
Oh, that makes sense. It pairs the signals.
Right. By moving to this architecture, the predictive power skyrocketed. The UIS 2023 research paper, that's the Workshop on the Economics of Information Security, demonstrated that EPSS version 3 improved prediction performance by an astonishing 82% over its predecessor.
82%.
The precision and recall metrics just went through the roof.
That is a staggering leap in accuracy. But even the best model is only as good as the ground truth data it's tested against. So it's scraping GitHub and IMOE, but how does it know if an exploit is actually happening in the wild right now? It has to pull in active network telemetry, right?
Yes, and this is the critical differentiator that separates EPSS from theoretical risk scores. It ingests daily observations from massive global sensor networks.
Okay, talk to me about the sensors.
We are talking about thousands of honeypots, IDS and IPS sensors, and active threat intelligence databases from major cybersecurity vendors. Organizations like Fortinet, Alien Vault, Grey Noise, the Shadow Server Foundation, they're all actively feeding anonymized detection data directly into EPSS.
Let's visualize that for the listener really quick. Grey Noise, for example, operates this massive network of honeypots, basically fake servers placed all over the internet designed specifically to be attacked.
They want to get hit?
Right, so when a threat actor writes an automated script to scan the entire internet for a new vulnerability, that script inevitably hits a Grey Noise honeypot. Grey Noise logs the packet payload, identifies the CVE being exploited, and feeds that raw telemetry directly into EPSS.
Exactly. So EPSS isn't just guessing based on text descriptions. It is looking at hard, verifiable evidence of malicious packets hitting sensors globally. But it also looks at human behavior.
Wait, human behavior?
Yeah, it parses social media chatter.
Mhm.
If security researchers, penetration testers, and threat actors are blowing up a thread about a new zero-day, the model incorporates that momentum.
I actually read a piece of research from Scientia and Cisco that blew my mind. They found that prioritizing fixes based purely on social media chatter, just looking at what InfoSec accounts are talking about, is actually twice as effective at reducing your organization's probability of exploitation compared to relying on CVSS.
It sounds crazy, but the wisdom of the crowd is real.
That is wild. But ETSS doesn't just rely on social media. It combines that human chatter with the hard network telemetry from the honeypots.
Right. And because it refreshes daily, it catches temporal trends that humans completely miss. Here's a perfect example from the Scientia Institute research.
Let's hear it.
As an industry, we tend to panic about the shiny new zero days, right? The moment a new CVE drops with a cool logo and a catchy name, everyone scrambles.
We love a good logo.
We do. But the EPSS data shows a completely different reality. 3 times more exploits target CVEs that are 10-plus years old than those published in the last 2 years.
Wait, really? 3 times more volume on decade-old vulnerabilities.
Yes, it's a momentum factor. Once an exploit is weaponized, and once it is integrated into automated scanning tools, botnets, and ransomware as a service platforms, it doesn't just disappear.
It just becomes part of the toolkit.
Exactly. Attackers are economically rational. Why spend thousands of dollars and weeks of time developing a novel exploit for a brand new vulnerability when an off-the-shelf 10-year-old exploit still successfully compromises 5% of the internet because companies have terrible legacy patching practices?
Oh man, that hurts because it's true.
The EPSS machine learning model captures this historical momentum perfectly. It keeps the probability scores elevated for older vulnerabilities that the honeypots still see active scanning for, while letting the scores of shiny new but non-exploited vulnerabilities decay rapidly back down towards zero.
Okay, this is brilliant. So we have this powerful predictive engine. The statistics are sound, the data pipes are massive and grounded in reality, but how do we actually use this?
The million-dollar question.
Right. If you are the listener sitting at your desk tomorrow morning, how do you build a remediation matrix without ripping out your entire tech stack and starting from scratch? Because you can't just tell an auditor, hey, the ML model told me not to patch this. You need a defensible process.
Absolutely. This is where we bridge the gap between theoretical data science and operational reality. You do not need to throw away CVSS entirely, and you certainly don't need to abandon your current vulnerability management platforms.
Okay.
Most modern commercial scanners, Tenable, Qualys, Rapid7, they already support EPSS API ingestion. What you need is a mature decision matrix. We call this the operational triad framework.
I love this framework because it's so practical and actionable. Let's break down the 3 pillars of the triad for the listener. Pillar number 1 is the CISA KEVI.
Right. The Cybersecurity and Infrastructure Security Agency maintains the Known Exploited Vulnerabilities Catalog, the KEVI. If a CVE is on the CISA KEVI, it is no longer a probability.
It's happening.
It is a documented, verified certainty. It is actively being weaponized in the wild, often by advanced persistent threats or ransomware operators. If a vulnerability hits this list, you bypass the ML predictions, you bypass the severity debates, you bypass everything. You patch it immediately, no debate.
It's the active threat pillar. It is the absolute floor of vulnerability management. If it's on the CISA heavy, your house is already on fire. So pillar 2 is where EPSS comes in. This is the predictive threat pillar. Let's say a vulnerability is not on the CISA heavy yet, but the EPSS score is screaming hot. Let's say it's in the 95th percentile or above.
In that case, you treat it as an imminent storm. The telemetry is showing massive attacker momentum, proof of concepts are likely circulating on GitHub, and the global honeypots are lighting up with scan traffic.
Even if CISA hasn't flagged it yet.
Right, even if CISA hasn't officially cataloged it yet, which, remember, can sometimes take days or even weeks of bureaucratic verification before they update the list. The empirical data says the wave is crashing right now. You prioritize it heavily, you patch it immediately alongside your KEV items.
And finally, pillar 3. This is where we still use CVSS, but we absolutely demand that it is combined with asset context. This is your environmental threat.
Exactly. We don't throw CVSS away, we contextualize it. Let's say a vulnerability has a very low EPSS score globally. The weather forecast says it's completely sunny. No attackers are actively using it anywhere. However, the vulnerability is a CVSS 9.8, and it exists on an internet-facing, mission-critical production database that holds your customer's unencrypted PII.
Right. If that gets popped, it's a front-page news event.
Exactly. In that specific scenario, the impact of a breach is catastrophic to your business. You prioritize it based on your internal environmental context, overriding the global probability. You are making a localized risk decision.
So to summarize the triad for you listening, active threats from the CISA KHEV, predictive imminent threats from EPSS at the 95th percentile, and catastrophic environmental risks from CVSS paired with critical asset context.
That's the blueprint.
When you combine those 3 pillars into an automated workflow, the efficiency win is just staggering. I want to share some hard data from the Security Navigator 2024 report in the WOI's research. By combining EPSS with standard workflows, security teams can slash their patching workload by up to 70%. Let me say that again for the people in the back. 70%.
And it requires roughly 1/8 the effort of typical legacy CVSS-only strategies, while achieving far better coverage of the actual real-world threats that will lead to a breach.
It's almost too good to be true.
You are fixing fewer things, but you are fixing the right things. You aren't exposing the company to extra risk by ignoring the rest of the backlog. You are actually heavily reducing risk by focusing your finite engineering resources exactly where the attackers are currently operating.
I want to be really clear about the human element here, because this isn't just about saving your company from a ransomware event. This is about saving your security analysts from burning out. It's about getting your weekends back.
That's the real ROI.
Seriously, it's about looking at a dashboard of 10,000 vulnerabilities, applying a filter that says EPSS greater than 0.10, and watching 8,800 of those alerts vanish from your immediate sprint. That is profound for team morale. It takes a team from drowning to swimming.
It really does. It shifts the entire team posture from reactive firefighting to proactive intelligence-led defense. But we promised our listener we wouldn't just be cheerleaders for this model.
Oh, yes.
We have to look at the flaws.
Yes, absolutely. This sounds almost too perfect, and any security professional listening is going to have their guard up right now. Where are the blind spots? Where does EPSS fall completely flat?
The most glaring limitation, fundamentally tied to its architecture, is zero-day exploits. By definition, a machine learning model requires historical training data to make accurate predictions.
And 0 days have no history.
Right. A true zero-day vulnerability is unknown to the software vendor, unknown to the public, and has absolutely zero historical footprint in the CVE database. EPSS cannot effectively predict a zero-day. It might show elevated risk for certain classes of software based on past trends, but it cannot foresee a totally novel, unannounced attack vector before it happens.
That makes complete sense. It's a predictive mathematical engine, not a crystal ball. But there is another really interesting critique that I read from the Codem security research that highlights a different kind of blind spot. They used a really brilliant analogy comparing EPSS to an ImageNet classifier.
Yes, I read that critique as well. It's a very apt comparison. ImageNet models are trained on millions of photos to recognize general objects. Dogs, cars, airplanes. They're great at broad, generalized categorization.
Okay.
EPSS is similar. It learns the general macro-level patterns of the internet, The core critique is that EPSS is all signal, no situational awareness.
Right. It predicts the probability of an exploit occurring anywhere on the globe against anyone. It does not predict the probability of a compromise occurring in your specific localized environment.
Exactly.
It doesn't know that you have a web application firewall in front of that vulnerable server. It doesn't know that you have strict microsegmentation or that a specific port is blocked at the perimeter.
It's the global weather forecast, not the microclimate in your specific living room. You still have to bring your own local context. Another critical bias we need to discuss, and this is a big one for mature security teams, is the ingestion bias.
Okay, tell me more about that.
Remember how we talked about the model relying heavily on ground truth telemetry from honeypots and network sensors?
Right. The gray noise and shadow server data,
Mm.
which naturally biases the entire model toward network exploitable mass-probed vulnerabilities, right?
Precisely. Think about how a honeypot works. If a ransomware operator or botnet herder is running a mass scanning script across the entire IPv4 space looking for an open Apache Struts vulnerability, every single honeypot from Alien Vault to Fortinet is going to get hit by that scan.
So it generates a ton of noise.
The EPSS telemetry pipes will flood with alerts, and the probability score for that CVE will skyrocket perfectly. But what about a highly targeted, highly sophisticated spear phishing campaign?
Oh, I see. Let's say an advanced persistent threat group uses a niche desktop software flaw, maybe a vulnerability in a specific PDF reader, to compromise a single executive's laptop.
Exactly. The honeypots will never, ever see it. The threat actors aren't spraying that exploit across the public internet. They're using it surgically via email against a single target.
Wow.
So highly targeted attacks or vulnerabilities in niche enterprise software that isn't exposed to the public internet might completely slip under the EPSS radar. The score will remain extremely low, near zero, even though it's being actively used in corporate espionage.
Which perfectly reinforces why we absolutely need the CISA and environmental asset context in our operational triad. You cannot rely on the machine learning blindly. If you know you have high-value targets, you have to measure risk differently.
You have to know your environment.
But there's one more fascinating paradox I want to bring up. I found this in the NIST Cybersecurity White Paper 41, NIST CSWP 41. It's about how EPSS functions as pre-threat intelligence.
Ah, yes. The LEV metric research. This is a brilliant nuance in how the data scientists actually designed EPSS.
It kind of broke my brain at first.
The creators explicitly built it as pre-threat intelligence, meaning they designed the ML model to predict future exploitation over the next 30 days, not to simply act as a historical record of past exploitation.
Okay.
In fact, if you read their technical documentation, they explicitly state that when they tried adding past vulnerability observation as a direct input feature into the model, it actually made the model less predictive.
Wait, why? If something was exploited yesterday, wouldn't that be the absolute best indicator it will be exploited tomorrow? Why would including that make the model worse?
Because it would cause the gradient-boosted trees to completely overfit to the past. The model would get lazy.
Lazy machine learning.
Exactly. It would basically just say, well, it was exploited yesterday, so it will be exploited tomorrow, and it would stop looking for the subtle precursor signals that indicate new threats emerging. By forcing the model to rely on precursor indicators like GitHub activity, age, and initial honeypot probes, it becomes much better at predicting the next wave.
That is incredibly smart data science. But it creates a bizarre paradox, right? For vulnerabilities that are already widely known to be exploited, the ones that are clearly documented on the CISA EPSS intentionally scores them lower than you might intuitively expect.
It does. It might give a highly famous, known, exploited vulnerability a score of 0.80 instead of 1.0 because the model is predicting the future 30-day window of activity.
So it's looking past the peak.
Right. If a vulnerability is old and everyone has already patched it, the peak of the attack curve is already passed. The probability of it being exploited tomorrow is actually lower than it was 6 months ago.
So how do we fix that blind spot? Because if an analyst sees a 0.80, they might deprioritize it, even though it's historically devastating. This is where the NIST researchers proposed a new mathematical equation called LEV likely exploited vulnerabilities.
Yes. The LEV equation basically looks backwards to solve the paradox.
Yeah.
It takes the entire historical sequence of daily EPS scores for a vulnerability since it was published and calculates the compounding probability that it has ever been exploited in the past.
Like a historical safety net.
It's a way to use EPSS data to mathematically catch vulnerabilities that might be missing from official CISA lists, but have a high probability of historical exploitation. It's a patch for that pre-threat intelligence blind spot. It really shows the industry is still actively, rigorously refining how we measure risk.
And that constant refinement is what makes this space so incredibly exciting. We are no longer stuck with CVSS static scores from a decade ago. We have dynamic breathing data that learns and adapts.
We finally have the tools to fight back effectively.
So let's bring this all home for you, the listener. Let's make this actionable right now. Your mandate for today is this. Stop chasing a CVSS 10 if the empirical research, the global honeypots, and the predictive models show that nobody is actively weaponizing it.
Stop burning out your teams for ghosts.
Go to your security teams tomorrow, look at your vulnerability management platform, see if it supports the EPSS API. If it does, turn it on. Embed daily EPSS lookups directly into your CI/CD pipelines and your triage dashboards. Let the machines do the heavy lifting of triage so your human analysts can do the heavy lifting of actual meaningful security architecture.
It's really about working smarter, not harder. You can't outpatch the internet. The math guarantees you will lose that race, but you can certainly outprioritize the attackers.
Absolutely. Thanks for tuning in to InfoSec Bytes. Keep exploring our 100-plus episodes on information security, AI, cloud, quantum, and cybersecurity incident root cause analysis. Please like, subscribe. We are on various platforms: Spotify, Apple Podcasts, YouTube, Amazon Music, and share to stay connected and keep your cyber defenses strong. See you in the next episode. Stay tuned.
And before you open your vulnerability dashboard tomorrow morning, I want you to ask yourself one final question. How would your entire security posture change? And how would your team's stress levels fundamentally drop if you assumed every CVSS critical was a false alarm until the EPSS threat data proved otherwise?